Hello you guys, how you doing today? And today we're going to talk about how to derive Young's modulus equation for springs. Young's modules. Young modules. I'm so sorry for my really bad pronunciation. But before we go see Young's modulus equation and what it is, we need to know what it stands for. And I want to give you right now a quick summary of it. Young's modulus stance is the ratio of stress to strain for a particular material, and it does not depend on the size or shape of the object. Now that we know a little about it, we can see Young's modulus equation. Young's modulus equation stands for F divided by A divided by delta L divided by L. Now, some of you would be like, oh my god, what is this? But it's okay, it's not that hard. That F stands for force, A stands for the area, delta L stands for the stretch, how much the spring is stretching, and L is the original length of the spring. Now, let's go derive Young's modulus equation. Now, with the power of our very powerful imagination, we're going to imagine that this right here, yeah, that line right there, that line is a spring. Yep, that's a spring. Now, Young's modulus, we need to go inside the spring. We want to go inside the spring. That's what Young's modulus is doing. You want to see the atoms. No, you just want to go inside of it. So I drew a 3D form of it. And in all that white space, that empty space, there's a bunch of atoms. There's a bunch of atoms here, on the sides, on the top, and everywhere. And they acting like springs. You know, they're holding each other and they're going all the way down, all the way to the side. Something like this. Yep, they look like this. You see those squiggly lines? That's all springs. Springs here, springs there. Now, if I were to put a weight right here, that weight, and right now, for this, I don't really care how much that weight weighs. I just know that if I put a weight, I get a delta L, that's the stretch, because my spring will stretch. I have my L, that's my original length. I have D is the diameter of every atom, and my A, that's my area. So, by definition, I can find force is equals to the spring constant K divided by multiple times S, and S is the stretch, delta L. So I can write this as, but I don't want this. This is for this spring right here. I don't want that. I want to find out the inner atomic spring constant. I want to find this. So to do that, I need to derive this equation by doing so. I know that K is equals F divided by S, and F divided by S is equals to mg divided by delta L. And I know that this is equals to NP Ks divided by Ns. Now, some of you would be like, Paolo, where are you getting NP and Ns from this equation? But it's not that hard. First, if you look at this, we know that parallels make parallels like this. That's our parallel springs have a higher spring constant. They're stronger. So NP will be equals A, the area, divided by the diameter squared. And NS stands for series. I have a series right here. They're lower. They have a lower spring constant. They're weaker. If I have 5 springs in series, that means they're 1/5 weaker. So NS has to be equals to L divided by the diameter of every atom. Now that I know what NP and NS stand for, I can include it in my equation as A divided by A times Ks divided by D squared times L divided by D. And I can cancel the D's to have A times Ks divided by D times L. And I know that this and this, yes, this and this are equals to each other, so I can solve for my Ks, and my Ks will be equals to Ng divided by delta L times dl times A. And now I can cross multiply them, And I get F is equals to mg. Remember, F, mg, they're the same thing. F divided by A divided delta L divided by L. That looks very familiar. That is just like Young's-Smallest equation. We did it. We just derived Young's-Smallest equation. Thank you.